Student friends, last time we have discussed the various theories of acid and bases, and then how the structural effect or effects correlates with the acidity and basicity, and which factors they affects on the relative acidity and the basicity. So today we are going to study or discuss the relative acidities of various acid and bases. So we start from the simple aliphatic acids, and we start from the example number first, 5 formic acid. 5 formic acid is stronger acid than acetic acid, because we compare the relative acidity between formic acid and acetic acid. We take here the formic acid and we dissociate the formic acid. After dissociation of the formic acid, there is a formation of formate anion and H plus. Similarly, after dissociation of acetic acid, there is a formation of acetate anion and the H plus or proton. So what happened? Means why the formic acid is a stronger acid than the acetic acid. So that's why we dissociate both the acids. This is a formic acid. After dissociation, there is a formation of formate anion, and formate anion is nothing but a conjugated base. Similarly, when we think about the acetic acid after dissociation, it gives the acetate anion. It is a conjugated base and formation of H plus. So what happened here? In case of formic acid, there is a hydrogen is a substituent, and in case of acetic acid, there is a methyl is a substituent. And we already know this methyl group donate the electron, and when methyl group donate the electron, it gives electron donating inductive effect, or it gives the plus I or plus I effect. And again the polarity between the OH bond is decreased, ultimately the dissociation is decreased, and the next important part, or similarly the conjugated acid or this acetate anion is destabilized, because we already discussed when there is a plus I effect is there, then conjugated base or acetate anion is destabilized, and when it destabilizes, then it reacts with H plus, and then the backward reactions are takes place. So the acetic acid is a weaker acid as compared to the formic acid. But in case of the formate anion, there is a hydrogen, so such type of plus I effect is absent in case of formic acid. So that's why the formate anion or the conjugated base of formic acid is not destabilized as like a acetate anion. So that's why the formate anion having the more stability as compared to the acetate anion. This makes formic acid is a stronger acid as compared to the acetic acid. When we think about various unsaturated acids, you take a next example, that is a unsaturated acid. When we take these three examples, this is the first one, This is a second acid, and this is the third one. And when we want to compare the acidity of these three acids, and we remember this is the first acid in which this acid group is attached to sp3 carbon, this one. In case of second one, this is attached to the sp2 carbon, and in third case it is attached to the sp carbon. So what is the effect of the hybridization of that particular carbon? First example, this carbon having the sp3 hybridization. In second case, this carbon is sp2 hybridized. In third case, this carbon having the sp hybridization. So similarly, what happened in this case, when we compare the percentage of S character, when the percentage of S character is increases, then the electronegativity of that particular carbon is increases, and this carbon gives the minus I effect, and acidity is increases. So that's why we remember sp2 carbon, there is a percentage of S character is 25%. When there is a sp2 carbon is there, percentage is 33%, 33.33, and when there is a sp, then percentage of carbon, percentage of S character is a 50%. sp2 hybridization, 25% S character. sp2 carbon, 33% of S character. sp carbon, there is a 50% of S character. And when we think about, when we go from top to the bottom, the percentage of S character is increases, and when the percentage of S character is increases, then what happen? The electronegativity of that particular carbon is increases. So when there is a sp3 hybridization, then this carbon gives plus I effect. When there is a sp2 carbon, then this carbon gives the minus I effect. And when there is a sp carbon, this carbon also gives the minus I effect, but the strength of minus I effect is more. So that's why in this case, what happened? Out of these three, this last acid or last one, it is a more stronger acid, because it having the 50% S character. S character is increases, electronegativity of that particular carbon is increases, and when electronegativity of that particular carbon is increases, then ultimately it gives the more and more minus I effect, and it gives the more and more minus I effect. It makes the last one or third one, this acid is a more stronger than second one, this is a more stronger, and which is the least stronger, this is the first one. So in this way we compare the relative acidity in case of unsaturated acids. Then in this case we take a next example, and substituted aliphatic acids. Substituted aliphatic acids. And for the substituted aliphatic acid, we take three examples. You take acetic acid, monochloroacetic acid, dichloroacetic acid, and trichloroacetic acid. And when we think about this particular acid and we compare the acidity between these three, so all that are the substituted acid. We remember in first case, this is the methyl donated the electron, it gives the plus I effect. When we think about the second acid, monochloroacetic acid, chlorine is electronegative, it gives the minus I effect because it withdraws the electron. In this third one, there is a such type of 2-chlorine is there. This 2-chlorine gives the minus I effect. So minus I effect is more. And in last case, there is a such type of 3-chlorine is there. And this 3-chlorine gives the minus I effect. So what happened? In first case, the methyl gives the donate the electron, it gives the plus I effect, electron donating inductive effect. So when electron donating inductive effect is there, then the acidity is decreases. Here is a 1-chlorine, it gives the plus I, minus I effect. In this case, the dichloro, there is a 2-chlorine is there, it gives the more minus I effect. And in last case, there is a 3-chlorine is there. So number of electronegative atom is increases. Then the minus I effect is increases, and when the minus I effect is increases, then this trichloroacetic acid is a very strong acid out of these 4. So trichloroacetic acid is more stronger, then dichloroacetic acid, then monochloroacetic acid, and then last the acetic acid is a weaker acid. So in this way, we compare the acidity between the substituted aliphatic acid. You take a next example and we change the electronegative atoms, or we change a substituent. So what happened here? You take the first fluoroacetic acid. Fluoroacetic acid. Then you take a chloroacetic acid. Then you take a bromoacetic acid, and you take iodoacetic acid. What happened here? When we change a substituent, means we change the electronegative atom. Here the fluorine, here the chlorine, here the bromine, and here the iodine. So what is the order of electronegativity? Fluorine is a more electronegative, then chlorine, then bromine, then iodine. So what happened? When fluorine is more electronegative, then it gives more and more minus I effect. And when it gives the more and more minus I effect, this makes fluoroacetic acid is a stronger acid. When we comes to the chloroacetic acid, so chlorine is also electronegative, but its electronegativity less than the fluorine. And when the electronegativity decreases, the minus I effect is decreases. So as compared to chloroacetic acid is a weaker acid because chlorine having less electronegativity, and ultimately it gives a less minus I effect than the fluoroacetic acid. Then in case of the bromine, also the electronegativity is decreases. It also gives the minus I effect, but the minus I effect is less. And finally we take a iodoacetic acid. In case iodine is the least electronegative, so the iodoacetic acid is a weaker acid and the chloroacetic acid is a stronger acid. So means what? When we change your substituent or we change the electronegativity of your substituent, then the minus I effect is changed and the acidity of various acid is increase or decrease. Then you take a next example, and here the distance between electronegative atoms, means we take these 4 examples. We take alpha chlorobutanoic acid, you take the here beta chlorobutanoic acid, here you take that is a gamma chlorobutanoic acid, this is a alpha chloro, this is a beta chlorobutanoic acid, this is a alpha, beta, gamma, gamma chlorobutanoic acid. So what happened? We compare the relative acidity between these three. So what is the important point here? From the electronegative atom, the distance is increases, then the strength of inductive effect is increases. Means what happened? The distance between this chlorine and this carbonyl carbon or acid group is increased. Then the strength of inductive effect is a decrease. So we remember here the distance between the electronegative atom and this acid group is less. Here the distance is increases, and in last case the distance is more and more. So what is the effect of distance of electronegative atom from acid group? So when in case of the alpha isomer, this is the alpha isomer and the distance is less, so this chlorine gives more and more minus effect. So what happened? Distance is less between electronegative atom, minus effect is more. Here the distance between electronegative atom is increases, minus effect is decreases, and in this case in a gamma isomer, the distance between electronegative atom is more and more. So ultimately here is a least minus effect or less minus effect. So out of that three, when we compare the acidity, it is a more stronger acid, alpha butanoic acid, because the distance between electronegative chlorine and the acid group is small, so that's why it having the more minus effect and the acidity is more. So the alpha chlorobutanoic acid is a more stronger acid, and which is the least acid, acidic, there is a gamma chloro, because the distance between this chlorine and the acid group is more. So ultimately the minus effect is less. So it makes, or this makes, gamma chloroacetic acid is a weaker acid out of these three. Then you take a next example, and we discuss about the phenols. And when we discuss about the phenols, so the question is that why phenols are acidic in nature while cyclohexanol is neutral in nature. This is your question. We compare the acidity between the phenols and cyclohexanols or cyclohexanol or alcohol. So we write the structure of phenol and we write the structure of cyclohexanol. We dissociate the phenol, we dissociate the cyclohexanol. After dissociation of the phenol, we get here the phenoxide ion. Or we call conjugated base. Then after dissociation of the cyclohexanol, we get here the cyclohexyl anion, cyclohexyl oxide. And we remember, once we get here the cyclohexyl oxide, and then we compare why the phenol is acidic and why the cyclohexanol is neutral in nature. So basic point, there is two reasons why the phenol is acidic in nature. So first we compare, when we think about this OH group in case of phenol, this is attached to the sp2 carbon. In case of cyclohexanol, this OH group is attached to the sp3 carbon. And we remember so many times or explain so many times, when there is a sp2 carbon, it gives the minus I effect, and when there is a sp3 carbon, it gives the plus I effect. So this is the first reason why the phenol is acidic in nature, because in phenol this OH group is attached to the sp2 carbon, and sp2 carbon exerts or gives the minus I effect. And in case of the cyclohexanol, this OH group is attached to the sp3 carbon, it gives the plus I effect. So we already discussed minus I effect, conjugated base is stabilized, and your compound is more and more acidic in nature. So this is the first reason. In case of phenol, OH is attached to the sp2 carbon, it gives the minus I effect. In case of cyclohexanol, OH group is attached to the sp3 carbon and it gives the plus I effect. So that's why the phenol is acidic, cyclohexanol is neutral in nature. But when we think about the stability of conjugated base, when in case of phenol, after dissociation it gives the phenoxide ion, it is a conjugated base. Cyclohexanol, after dissociation it gives the cyclohexyl oxide, it is conjugated base, and in which case the conjugated base is stabilized. So we remember, in case of phenoxide ion, this phenoxide ion is well stabilized by the minus R effect of ring system. Means minus R means the electron withdrawing resonance effect. So how this phenoxide ion is stabilized? So we able to write a resonating structure like this, and then we write the resonating structure of this phenoxide ion. Again we write another resonating structure. These electrons are given to here, and then we able to write the resonating structures. So negative charge goes to here, we write here. So means what is your reason? Because in case of phenol, after dissociation of phenol we get a phenoxide ion. Phenoxide ion is a conjugated base, and this conjugated base is well stabilized by minus R effect of ring, minus R effect of benzene ring. So this is important. Means what? The phenoxide ion is well stabilized. We already discussed, or we explained so many times, when the conjugated base is stabilized, either minus I or minus R, then your acidity is increases or acid strength is increases. So the phenoxide ion is well stabilized by the minus R effect of a benzene ring, like that, and that's why the phenol is more acidic and cyclohexanol is neutral in nature. What happened in case of the cyclohexanol? So this cyclohexyl oxide is not stabilized as like a phenoxide ion, and this makes the phenol is acidic in nature and cyclohexanol is neutral in nature. So in this case we compare the acidity between phenols and alcohol, or phenols and cyclohexanol. We take a next example and we compare the acidity between the phenols and nitrophenols. We take a simple example. We compare the phenols and nitrophenols. So what happened? We take a first example, that is a phenol, and we write all nitrophenols. We write a orthonitrophenol, we write a metanitrophenol, and we write a paranitrophenol. So we compare the acidity between the phenols and nitrophenols. So we remember nitrophenols are always more acidic than the phenol. Why? Because we remember in case of nitrophenol, there is a nitro group. And what happened? Nitro group is the electron withdrawing group. It withdraws the electron. So this nitro group gives the minus I as well as the minus R effect. So that's why all the nitrophenols, you take an example of orthonitrophenol, we take an example of the paranitrophenol, we take an example of a metanitrophenol. All the nitrophenols, they are more acidic as compared to the phenol because they are having the nitro group. It also gives the minus R, means electron withdrawing resonance effect is there. So that's why all the phenols, nitrophenols are more acidic as compared to the phenol. Once you discuss the acidity between the phenols and nitrophenols, then we compare the acidity between these three phenols. And what happened when we compare the acidity? So out of that three, which is more acidic? So we remember what happened in case of the orthonitrophenol, it gives the minus I. In case of the metanitrophenol, there is minus I effect is there, but this minus I effect is less because what happened here, the distance is small, minus I effect is more. Distance is increases, minus I effect is decreases. Again the distance is increased here, so the minus I effect is less here. The minus I effect here is more, and here the minus I effect is moderate. So what happened in this case? Again, we remember what about the minus R. So in case of orthonitrophenol, nitro group gives the minus R effect. In case of metanitrophenol, there is no minus R effect. That is important. Means in metanitrophenol, nitro group don't gives minus R effect. So that's why in case of metanitrophenol, nitro group only gives the which effect? There is a minus I effect. When we think about paranitrophenol, and in paranitrophenol there is a minus R effect is there. So what happened? So out of that three, which is more or which is the least acidic? Ultimately there is a metanitrophenol. So why the metanitrophenol is a more least acidic? Because what happened? In case of metanitrophenol, only there is a minus I effect is there, there is no minus R effect is there, and that's why the metanitrophenol is a least acidic out of these three. And why? The next question is there. Why in case of metanitrophenol, nitro group don't gives the minus R effect? Because we remember, so that's why we write a resonating structure of that phenoxide ion, and the negative charge on this oxygen is not delocalized on a nitro group, or nitro group is not taking part in a delocalization. And when the nitro group is not taking part in a delocalization, ultimately this nitro group don't gives the minus R effect. But what happened in case of the ortho and para? In case of ortho and in case of the para, nitro group is taking part in a delocalization, and when the nitro group is taking part in a delocalization, then nitro group gives the minus R effect. So this is the basic reason why the metanitrophenol is the least acidic out of these three, because when the nitro group at a meta position, it don't gives the minus R effect, and when it don't gives the minus R effect, then the metanitrophenol is the least acidic as compared to the orthonitrophenol and the paranitrophenol. Once you compare the acidity between these three, so which is the least acidic? Metanitrophenol. Then we compare the acidity between these two. There is orthonitrophenol and there is a paranitrophenol. When we compare, the minus I effect is same in both the cases. Here is a minus I effect is same, means in ortho, in para, minus R effect is same. But in case of the orthonitrophenol, minus I effect is more, here the minus I effect is less. even though the para-nitrophenol, it is a more acidic as compared to the orthonitrophenol. When we compare the minus R effect between these two, the minus R effect is same or equal. When we consider about the minus I effect, in case of the orthonitrophenol, minus I effect is more, and when we see the minus I effect, then we see the orthonitrophenol is more acidic. But actually this is not happen. And why this is not happen? Instead of orthonitrophenol is more acidic, there is a para-nitrophenol is a more acidic is there. So there is a introduction of a new effect that is called as a hydrogen bonding. And when we see in case of orthonitrophenol, we write a structure of orthonitrophenol. And what happened? There is a intramolecular hydrogen bonding. Means what happened when we think about this position of oxygen OH group and nitro group, they are come closer. So there is a hydrogen bonding. And when there is an intramolecular hydrogen bonding is there, due to the hydrogen bonding, what happened in case of orthonitrophenol, the dissociation of OH group is decreases. And when the dissociation of the OH group is decreases, then ultimately the acidity of orthonitrophenol is decreases as compared to the para-nitrophenol. But what happened in case of the para-nitrophenol, the distance between OH and nitro group is apart, or OH group and nitro group, they are apart from each other, and we are apart from each other, so there is a hydrogen bonding is not possible, and that's why here the dissociation is very easy, but here the dissociation is slightly difficult as compared to the para-nitrophenol, and this makes the para-nitrophenol is more acidic as compared to the orthonitrophenol.